Evening, everybody. Welcome to another episode of the ESP32 product journey. My name is Kevin, and we're going to pick up right where we left off last time. For those that are just joining for the first time, we are creating an Internet of Things product from an ESP32 module, specifically the ESP32 Room module. And the product that I'm making is a hockey puck holder that will display stats for your teams. In fact, my original version of this was a hockey puck, real hockey puck there with the display in it. It actually just updated with my team, pulled off a big win tonight, Washington Capitals. So I'm really pumped about that. But we got some work that we got to do. We're actually behind schedule on this. We're trying to get puck holders released for the start of next season, and we've got a ton to do. On the last episode, we got FTX Prague working on Linux, which is what I would prefer to use it on. We're going to have to make a pull request to that, some code changes to actually configure our FTDI device for our needs. We'll do that in an episode coming up. And we still need to solve the charging problem. And so to give a brief overview for those that may be joining, let's come over here to the schematic view of this. It's a little, we'll zoom in here some. There we go. Right here on the left, we've got our USB in. That's our micro USB port comes in. Right in here, we turn the USB data into an RX and TX symbol. We do that with an FTDI chip. And up here, we have the power block. So the 5-volt comes in from the micro USB. And then if we come into this part of the data sheet, it goes through a PMIC there that can power the device as well as charge the battery. Goes through a linear voltage regulator that spits out 3.3 volts. And that's what we use to power the rest of the hardware. So if we come back out and we come into the USB block, you can see this is just the FTDI chip. And what we talked about last time was using these CBUS 0, 1, 2, and 3 pins on the FT231XQ that we're using to help us determine charge levels and charge current and things like that, given the different states that our device could be in when connected to a USB port. As a quick reminder, we don't have a ton of time to recap this, but you can plug a USB device into a dedicated charger, like this Android charger right here, or you could plug it into a powered hub that has its own power supply. You could plug it into a self-powered hub, which is getting its power from the main computer that you've connected it to, or you could connect it to a regular USB port. That USB port could be a USB 2.0 port, which has a 500 milliamp max current limit, or it could be a USB 3.0 port, which has a max current limit of, I want to say, 800 milliamps. So there's all of these different charge limitations. When you first plug it in, before the computer has a chance to enumerate it, you can only draw up to 100 milliamps of power. When the computer goes into standby and suspends all connected USB devices, you are only allowed to consume 2.5 milliamps of current. And so we have current requirements all over the map for what our device can draw. And if we want to be compliant with USB spec, we need to meet those. Currently, my puck product does not meet those. It will just pull whatever amount of current it needs up to probably around the 400 or 500 milliamp range. And a computer and the hub, because I plugged it into both, will not stop you from doing that. It could, and it might shut down if it over currents, has too much current being drawn from it. But so what we're trying to do is make the puck holder compliant with all of those different scenarios, but also be able to charge a bigger battery that we have put into the design. So that's where we're at. That's a quick recap. Now let's get right into it. Since our last video, I made a table. And I cover all of the scenarios that we need to support. And so they're listed right here along the left. We've got plugged into charger. That's plugged into one of these. Plugged into a USB port and enumerated. There's a difference because, as you'll see, I put the USB spec current limit right here. When you're plugged into a charger, there's no limit. Just the limit is what the charger can provide, and if you request more than that, you won't get it. So there's no limit there. When you're plugged in and enumerated, you've got a 500 milliamp current limit. When you're plugged in and the host has put the device into suspend mode, you have a 2.5 milliamp current limit. And if you're plugged in before enumeration to a host, you have to limit to 100 milliamps. So I translate those into my max current needs for our puck holder. Now, when we're plugged into the charger, I set that to 900 milliamps. Really quickly, the way I came up with that is I'd like to set the fast charge current to around 400 milliamps. That will charge our battery in about 4.5, 5 hours. And I want to have the ESP32 data sheet says the external supply should supply at least 500 milliamps of current. So I want to have 500 milliamps available in addition to the 400 that I'm charging with. When we're plugged in and enumerated, we can request up to 500 milliamps. And so I'm going to set the max current to 500. When we're plugged in before enumeration, 100. And when we're in USB suspension, 2.5 milliamps. Now, the PMIC that we have chosen, the BQ240, I always forget it. We'll say the BQ2407. That's what it is. The BQ2407 has some really handy built-in features. Let's bring the data sheet back over so we can remind you of that. Scroll down here. It already knows about all these limitations for USB current. And so you can see right here, based on the enable 1 and enable 2 pins on the PMIC, we can just pull those a certain way, high or low. And then right here, it says this will be USB 100 mode. It'll only take 100 milliamps, or 500 mode, 500 milliamps. This is what we currently have it as, which is it's set by an external resistor combination, and then 1 and 1 is standby, which means it's only going to draw 2.5 milliamps. In all of these scenarios, the PMIC will take whatever power it needs from the battery. So this is just limiting the input current from the USB source that we've plugged into it. So where have we landed with this? We need to get this designed in. Well, based on these scenarios, this plugged in, enumerated, I enumerated out what the different state of the BCD, power enable, sleep, and this is power enable again, pins on the FTDI chip could do. And then I showed what I want the enable pins to look like on the PMIC. And this is the charge enable pin on the PMIC. So these E, F, and G right here, these 3 columns are based on the different USB modes. This is what I need to do with the enable and charge enable pins on the PMIC. And this is what the FTDI pins will do in those scenarios. And lining them up side by side like this really helped so that I could see, is there an obvious way to use these pins to control the PMIC? And I think we have a way forward. And so I want to talk through that. If you'll look here, so let me first go back and talk about some decisions that I made after the stream last time. So what we can do is once we're enumerated, we can request up to 500 milliamps, but do we want to charge? Like what I needed to decide was, do I want to charge when I'm connected to USB? And I had before had this right here set to 180 milliamps. 180 milliamps. But then I thought, the most current we can draw is 500 milliamps. If I'm charging with 180 milliamps, the FTDI chip takes about 9. We'll round that up to 10 milliamps. I'm at 190 milliamps. Add in a couple of other things like the display. I'm at 200. That leaves me 300 milliamps for the rest of the device. So that includes Wi-Fi. And in the data sheet for the ESP32 module, Wi-Fi can pull up to like a max peak, like 369 milliamps. It averages more around 250, so I think we'd be okay here. But then I thought, why risk it? And do I really expect people to charge it from a USB port? And the decision I came up to yesterday was no, we're not going to do that. We're going to make it very clear in the instructions that this needs to be charged with a dedicated charger. And even as I'm saying that, like I'm worried about it. But let me talk through where I got. It's like, oh, if they plug it into a computer, I want it to charge. Well, to be safe, I would need this to be down closer to like 100 milliamps, right? And at 100 milliamps, it's going to take 18 to 20 hours to charge it, which means now I've got to change the timer on the PMIC to be like infinity long. And is somebody really going to leave it plugged in for 20 hours? Even at 180 milliamps, that would have to be plugged in for 10 hours to charge. It just seems like, make it clear you need to charge it with a dedicated charger. And if I have to, we could potentially supply that, although I don't think we need to. I think everybody has one of these. And at that point, we can supply a cable, a USB to micro USB, and even it looks like the newer Samsung phones come with a USB-C charger. So instead of the USB-A that's on the side of this one, I don't know if you can see that, kind of that angle. It just has a USB-C like on the front face of it here. And so it's no problem for me to stick one of these and a USB-C to micro USB cable in the box so people can use their phone charger. And so at this point, we're going to go with, you have to charge it with a dedicated charger, and we're going to say that the charge current does not apply at all when you're connected to a USB host. So we don't have to worry about charge enable, and you can see here, charge enable is 0 only when we're connected to a USB dedicated charger, and it can be pulled up to 1. Not applicable here is because I put not applicable here because when the PMIC is in suspend, it ignores charge enable. So it doesn't really matter what charge enable is here. We could just make it 1, which means don't charge. And then the enable pins, again, will satisfy the current requirements for USB. So with the charge enable pin like this and the enable 1 and 2 pins like this, we meet all the requirements for USB spec, and we only allow charging when it's plugged into a dedicated charger. Now, if we look at the way that the charge enable and enable 1 and 2 line up with what the FTDI chip does, which again is these, we'll just ignore this. Matter of fact, let's just get rid of it. We don't need a power enable 2 down here. High Z means it's floating, like the pin is neither high nor low, it's just left in a floating state, and you have to provide a pull up or a pull down resistor. And so let's talk through this and see if we see a pattern. So we need, in this state, we need 0 and 1. Well, we've got 0 and high Z. In this case, we need a 1, 0. Well, we have a high Z and a 0. So like the 0 is here and there. In this case, we need a 1 and a 1. In this case, they're both floating. And so if we were to put a pull up on enable 1 and 2, so a resistor, let's come over to the schematic. Come into here. Right here, you can see currently I have enable 1 pulled to ground, and I have enable 2 pulled up to 5 volts, pulled high. So enable 1 is low, enable 2 is high. Enable 1 is low, enable 2 is high, which means we're always in the we're always in this scenario right here where the charge current, there's not the charge current, I apologize. The maximum input current is determined by the current limiting resistor. And that's going to be, again, this 2.2K resistor right here. We want that to be the case only when we're plugged in. Otherwise, we want to use the enable pins to meet USB spec. So if I put a pull-up resistor on both enable 1 and enable 2, it will default to this suspend mode, which means it will draw virtually no power from the USB input when it's plugged in, and will get everything it needs from the battery. Great. And then when the FTDI enumerates, you'll see it's going to pull the power enable pin low. We can set that to CBUS 1. And then that's going to pull our, and if we connected that to the enable 2 pin, and we connected this BCD to the enable 1 pin, those would correctly pull things down when the chip starts up. So what I'm thinking is pull up resistors on enable 1 and 2, which will leave us defaulted in this state. And then we'd also connect we'd make CBUS 0 this BCD, the dedicated charger indicator, and we'd make CBUS one, the power enable, and we'd also connect power enable to enable 2, and we'd connect the charger detection to enable 1, and that would be able to pull it low to create these other scenarios. Now, what am I concerned about with this approach? One very important thing. So these limit the input current to the PMIC, which means whatever it can't get from the micro USB, it's going to get from the battery, which is fine. So at worst case, if the PMIC USB input's disabled, we're running on battery power always. And while not ideal, it would be nice when we're connected to some sort of USB to get power from that USB so that we don't have to use the battery. And that includes when you plug it into a computer. However, you can see here I have charge enable 0 only in this configuration. And what we could do is also run our CBUS 0. We'd probably actually duplicate it on a different CBUS pin and have this pull down our charge enable. So our charge enable right now, if we come over here and look at it, charge enable is pulled down through a 100K resistor right here, which means charging is enabled always. And what I'm proposing is we pull it up instead, so charging is disabled, and the only time it'll get pulled down to enable charging is when we're connected to a dedicated charger. And the worry that I have with that is the FTDI's ability to detect a dedicated charger. So if I understand this correctly, the way that USB to spec dedicated chargers work, which I'm assuming something like this meets that spec, I suppose I could test this. We might have to break out the meter in just a second and test this. Is it shorts through a resistor the D plus and D minus data lines, and that is what signals downstream to whatever connects to it, like, hey, I'm just here for power. I will never have data for you. I am a dedicated USB charger. My concern is cheap knockoff, you buy it at the rack at Walmart while you're checking out, USB charger. Is that going to register as a dedicated charger? Because if it doesn't, and it does not pull this CBUS line down to 0, charge enable will never be asserted, and therefore the battery will never charge. So I'm a little concerned about that. And the way that I think we can get around that, well, not get around it, is we're going to do it and we're going to test it. Like, I will find as many of these. I will buy one from the checkout at Walmart, and I'll buy one from the checkout at another place, and I'll order a bunch from Amazon and just see, if I have 10 or 15, I'll borrow one from anybody that's got one, friends, family, and test every single one of them to see if they register as dedicated charging ports. If I'm batting 1,000 on that and they all turn out to say, yep, the charge enable works and they're charging, then I'll feel good. We'll move forward. If I'm getting a failure rate of like 10, 20, 30% where it's like, some of them do, some of them don't, then we got to scratch this whole plan and do something different, which is going to really suck because then we'll have to do another hardware run. So I'm kind of banking on this working and dedicated chargers actually following spec. And again, if we run into just one-offs not working, because most people are just going to use their phone charger. They're going to use their Android charger. They're going to use their iPhone charger. And if those, by and large, work, then I think we'll be okay. And we could just have an FAQ that says, hey, if it's not charging, get a different charger and deal with that. Like, I don't want to spend too much more time thinking about this because I don't know, again, we could squeak out some current here, but even if we could, just to be like, worst case scenario, plug it into your laptop and it'll take 20 hours to charge. Like, but not really, because then you have to leave your machine on for 20 hours. Because like eventually they're going to go to sleep. The computer's going to go to sleep. It's going to throw it into suspend mode. It's going to drop the current down to 2.5 milliamps. It's not going to charge anyway. So like a 20-hour charge connected to a computer is, in my opinion, not an option. If you disagree, tell me. Like, tell me I'm crazy and that the way I'm moving forward is insane, and I'll rethink it. But I think we've got a good way forward for now. And so all we need to do now, we need to set the max current with the resistors to 900 milliamps and the fast charge current to 400 milliamps. So that's going to be this other spreadsheet that we have that I still have not cleaned up, where we can set the current set and current limit resistors. Yeah, see this, we changed this to 2200. Let's just do it right now. That's 731. What did I say I wanted it to be? 900 milliamps. So we're going to have to come up with like some... You know what? This is back to my tip that I gave 2 videos ago, where it's like, if don't create an extra part if you can reuse another one. Well, I'm going to take my own advice. This is going to need to be somewhere in like the 3000s. So let's just say like, not 3000, like 2100. Nope, not enough. 1900. Yeah, we're getting closer. Keep forgetting if it's 8 or 900. 900. Okay, so 900 is going to be somewhere around 1.9K. And if we look at our bill of materials, we do not have... Let's look at our resistors and see what we've got. 2.2 and 1.5. So we would have to create a new resistor value. I don't want to do that. I want to try and reuse. And this is a case where I can reuse, because if we limit the current, if it's 900, great. If it's an amp, great. So let's change this to 1500. 1500 is going to give us just over an amp current limit, max current limit. And you can see here our fast charge is set at 404 milliamps, and that's with our 2200 here. So let's start making changes. Let's start implementing these changes. One thing I'm a little concerned about is the step feeder hardware. Like, we made a bunch of changes here. Ugh. Rescue main CADs tab. Oh yeah, that was when I output it. Symlib table. Let's like do git diff EDA USB. So like, oh, this is, it changed main rescue. This is because I loaded some new stuff. I don't like it that it's calling it main rescue. That's weird. And what about power schematic? Same thing, huh? The linear regulator was changed to be something different. Okay. And then the lib. Let's look at it. Git diff EDA main cache lib. Main res. Okay, it's just changing it. Why is it calling it main rescue? Okay, well, I don't love it. The linear regulator and the micro USB connector. Let's look at it before we get too far into this and wish we hadn't have started making other changes. So the linear regulator here, if we edit this, package, library reference. See, like, I don't know why it says main rescue. Let's just do a search for XC622. Yeah, like, I don't know why we want it to be main rescue. Like, what if I say okay to this? And say okay. Like, do I still pass electrical rules check and everything? Yes. What is this going to tell me? Nothing should have changed there. Continue with how, yeah, it's going to tell me like 100 things are unconnected. Yeah, okay, but there's no problems. Okay, so now if I save this and then do this diff again, like I want to make sure that see, that made it, that cleaned it up actually. Now I don't have that main rescue deal. Okay. Yeah. And if I do alias, yeah, that cleaned main rescue for the micro USB connector. Yeah, okay. So we do want to fix that. USB. So USB still has the main rescue on that micro USB micro connector. So let's fix that. Before we move on, let's fix it. So the main rescue feels like a one-off thing that's going to bite us later. So right here, the footprint, the library reference is main rescue. So let's do USB micro connector. And that looks an awful lot like the same. We'll say, okay. And we'll say, okay. Let's check the DRC. Finished. Right. And now it's just, we just changed the reference. We don't have some other crazy thing. And then let's look at main lib, nothing, like no crazy changes there. Okay. That's exactly what we want. And the sim lib table. Yes, yeah, I don't think I need that main rescue lib and DCM. Do we? This isn't really what I wanted to spend time on, but we need to make sure this is right before we start making changes. Sim lib. Oh, because it's new. It's untracked. All right, I'll come back to that later, but I don't think we need this main rescue DCM or lib. EDA main.pro. As long as we don't reference it, I think we're okay. And main PCB. We did move a bunch of stuff here, so that's not unexpected. Okay, cool. We're moving on. Exit. Let's make these changes that we're going to make. Okay. Because it's getting late. Okay, we don't have to change anything here. But what we do want to change is those resistors. So let's come into the power block and let's change. I set, okay, fast charge is that, pre-charge, and then the time charge we can change. 9.5 is going to be too long now. We don't need it to charge for that long. But let's change limit to 1500 and set to 2200. Limit to 1500. Value 1.5K. Which means we're also going to need to change the description and part number. Okay. So let's just do okay for now. And then what did I say the other one was? Set to be 2200. 2.2K. And that's going to drop that unique 4.99K resistor from our bill of materials. So that's great. 1.5 to 2.2. And let's come into the BOM here. Non-resistors. I feel like we had another, yeah. These are both 1.5K. No, one of them's 1. Yeah, so let's come into here. Yep. So R4, we have changed to 1.5K. And so we need to change it to that, and the part number will change as well. Great. And then if we collapse that, now we shouldn't have that different. Yeah. So we have two of those now. And then the other one that we changed was R1 to be 2.2. Oh, I just swapped one for the other. Daggone it. I'm going to hit cancel. Discard changes. I just traded one for the other. R1 is now 2.2, which we want it to be. So we need this 2.2. Here we go. Let's grab that. Change it to be that. Then we'll take the 1.5 and make it here. So this should be a great illustration of why you want to keep this BOM part count low, because you've got to keep tracking these. So now I have 3 1.5K resistors. Is that true? No, just 2. It's just okay. And now they're all good there. And now we have a 2.2 up here. And now we no longer have a 4.9. Okay. 1.4, 2.2. And then we'll change timer later. Bellum, hello. Thanks for joining. All right, so let's start making these other changes. Come back over here. Again, we want to pull charge enable high. This does scare me, but we're gonna do it. The question is, what do we want to? I am making a product, a piece of hockey merchandise based on an ESP32. So I originally made this. It's a hockey puck, like a solid rubber hockey puck that we machined out, and we just stick an e-paper display in there, and it will update with team stats after every game, getting into player stats as well. And what we're doing now is making here's half of it, a different version of that, which is essentially a puck holder that looks like this, and then the display will go in here, and it'll hold a puck that's signed by your favorite player or whatever it may be. And so that's what we're working on. And we are working on modifying, here's the actual board that goes inside of it, working on modifying the charge circuitry on it right now as part of a few tweaks that we're making to the hardware before we send off another run. So anyway, cool stuff. It's ESP32, working in FTDI chips, power management chips to charge a LiPo that goes inside of it because it's battery powered. So all that kind of stuff, and hopefully other people find some of this interesting and helpful for their own projects. And right now, we need to decide where we want to pull charge enable. Do we want to pull it to 5 volts? We need it to be pulled high. Well, yeah. We want to pull it to 5 volt. Okay, So let's start making some of these. Oh yeah, man. If you're looking for IoT, you've come to the right place. So ultimately, where this is all headed is we're doing the hardware, sending that off, getting fab and assembly done. We'll be doing enclosure stuff, making orders on that, and then writing firmware for it. I've got a back end written for all of this that I'll also be streaming on. So it's like the whole front to back, hardware to back end. I'm trying to document all of it because I think it's cool, and I don't think a lot of people are showing the process as part of that. And I'll remind everybody that's watching, I'm doing this on my own personal budget. So, like, unlike a lot of hardware startups that get, $2 million in Kickstarter funds and then blow through it because they have no idea how to make an actual hardware product, or just get a large chunk of VC money and can blow it, I'm trying to prove a thesis that I have that you can actually do this on not a minimum wage budget, but on a normal person affordable budget. If you can, scrape together, I'm talking on the order of thousands of dollars, low tens of thousands of dollars, start to, product that you're shipping versus the hundred or millions of dollars that companies spend on this sort of thing. So I'm kind of trying to prove that thesis, and I'm either going to crash and burn and prove that you can't do it, or I'm going to prove that you can do it. So hopefully the latter on that. All right, let's start deleting. This is where it gets scary because once you start deleting stuff, it's real. It's been such a while since I have done KiCad, so we're gonna have to get back into. Yeah, I just want to copy it. Get back into the groove here. I believe W is wire. And we'll come out to that. Great. So pulling charge enable up. Let's look at our chart again. It's going to be pulled up, and the way we need to pull that down is from one of the CBUSs. So we'll get to that. And now we need to handle enable. Okay, and the other thing we were going to pull up is enable 1 and 2. Okay, so let's do that. So enable 2 is already pulled up. And for enable 1, let's just, oops, not edit. Let's delete this ground here and get our wire and just do that. So enable 1 and enable 2 are pulled up. And then what we want to do is right here, we'll want to put our symbol, like our CBUS line. Let me think about that for a second. Because now that they're pulled up, so charge enable again is active low, so it needs to be low to enable. And so I think we'd put the we'd attach the CBUS right here, and the same thing with enable. It wouldn't be over here. Like, you don't want to pull it down. Yeah, pull those up, and then we would just need to create like a label here, like we did over here with charge and pgood. Okay. These pulled up, enable's pulled up. Let's save those changes. So we've got all 3 pins pulled up, and now we just need to, I think we're going to reuse CBUS 1. So CBUS 0 will do BCD. So let's just do this. Let's come into here. We need to come back over to our USB serial part of the data sheet. Why is that not going in? Oh, because I'm in wire mode. Okay. So let's remove these do not connects on the CBUSs. And we're going to use 3 of them. I hope this doesn't complicate the layout too much. No connect, delete, no connect, and delete, no connect. And what we'll do, I can't remember, are these... these are these global? I can't remember. Can't remember how we did that. Hierarchical label. Yeah. Hierarchical label. We want to do a hierarchical label right here. We'll do it out here like we did with the other ones. What? Why you no place? Oh, that is a knock on my door. Stand by. Okay. And the label for this is going to be BCD1. And if you put the tilde, I'm not sure how you pronounce it, but if you put that, well, actually, let me leave it off first because this is kind of cool. And you'll see it's just BCD1, and I want this to be, I want the orientation to be right, and the style is, it's not really bidirectional, it's an output. So that's how we want it to look. So it looks like that. However, the charge detect on that we want to use is actually that pound symbol. I talked about this in the last stream. The pound symbol means it's active low, which means it asserts, like it will go low when it detects that it's connected to a USB charge port. So another way that we represent that in schematics is like you can see on this DTR line up here is with the line above it. Same thing for RTS. You can see that TX and RX transmit and receive are just normal, like high is high, low is low. For RTS and DTR, they're active low. And so you can see that also on the different chip schematic things here. Reset is an active low. And so you will see that it is actually pulled high to prevent you from resetting. And so if this gets pulled low, active low, it'll reset the chip. So one of the ways you can do that in KiCad is if you put a tilde in front of it, in front of the name, you'll see it'll put the line over it, which is pretty cool. And we'll just line this up with the rest of them. And we're going to use this twice. And it keeps all those. No, it doesn't. Right. Output. And we'll call this BCD2. And then the other one is power enable, which is also active low. So let's do one more in here. Power enable, right output, great. Great. And then we'll wire these up. Okay. And we'll leave CBUS 3. We don't need CBUS 3. I thought about actually using this sleep because if the device is suspended, we could use the sleep pin to say, like, if somebody did leave it connected to their computer, we could use that in the firmware. I'm not going to mess with it for now. We'll just leave it for now. Okay. So I think that's all we're going to need. We're going to need BCD1 and then BCD2. Now, there's actually only, again, if we look at the, oh, where do I have it? The data sheet. I'm not going to pull up the data sheet. I'll just tell you. You can configure the CBUS, these pins, CBUS 0, 1, 2, and 3, to have any number of functions, but you can also have multiple pins be the same function. So if I wanted to use CBUS 3 to have another power enable, I could do that. And they would they would perform the same way. And the reason you would do this is if you're driving a signal with one of them and driving a different part of the hardware with the that you want to use the same signal for, but you don't want to use the same electrical connection. You can do what I'm doing here, which is both of these, BCD1 and BCD2, will behave exactly the same. I'm going to connect them to different parts of the circuit. Again, based on this table, I'm going to use one of them to pull charge enable low, and I'm going to use the other one to pull this enable 1 low. I could probably use the same one. Let me think about why that might be bad. I don't think that that would be bad. And in fact, that might actually simplify the layout. Because right now, we're going to take a quick detour over to the layout of this. Right now, the FTDI chip is this guy right up here. It's got the 21 on it. And the PMIC is way down here. I try to keep the PMIC as close to the ESP32 as possible. And right now what we're saying is we're going to have to take one of these CBUS pins, which right now are electrically left unconnected. They're not labeled yet. And run it all the way down here where you can see it's already extremely crowded. And so if I only had to run one down here and then I connected them together. Do I really need 2 BCDs then? That's a good question. I don't know the answer to that. Let me just come in and look at the power block here. Oh, dang it. I don't know how to get back. There we go. So if we just said we're going to connect one of them here to enable 1. And then also, ground is ground. If it's going to drive it low, like whether CE is, yeah, no, forget that. We're going to use the same pin. I think that'll work just fine. Ground is ground. Like whether they're connected to different pins on the FTDI, they're both electrically going to be pulled low, which means continuity-wise, they're at the same potential. So there's no reason for me to run 2 lines. Done. It's a done deal. Forget BCD2. As quickly as it came, it left us. And we're actually going to throw a no connect back on there. And let's rename it. Instead of BCD1, we'll just call it BCD. Cool. And then now what we can do is we can come back. Oh, nope. Where am I going? We're going to have to wrap this stream up momentarily, about another 10 minutes or so. We'll come back into the power here. Oh, I just put a no connect in the middle of that. Not what I meant. And now power enable needs to go to EN2. Okay, so power enable goes to EN2. Let's do that. I believe it's just as long as it has the same name. Power enable. And it is a... Maybe I should say it's actually a tri-state. That's technically what it is. And I want it to go left. And I should change the other one. Yeah. So what a tri-state pin means is that it can be either floating, driven high or low. And so It's not just an output. In fact, it has, yeah, it's tri-state. That we should, let's make sure we get that right. So what we'll do is we'll come in here and we'll edit these to be tri-state. Okay, that's right. Come back into the power block, and then let's test this to make sure I'm thinking about it correctly. We said EN2, right? Power enable 0 EN2, yes. Just grab it. It's gonna get messy down in here. There is a drag G. I want to do G. G. Let's slide this way. And let's slide this way as well. And I'm going to just put that inside there like that. Uh, 10K and 10K. Trying to clear out some room here. Let's drag it a little more. Oh no, grab. There we go. Okay. And then now what we can do, now, yeah. It's getting a little crowded there. So you want these to be not super hard to read. I don't know that I like the R10 inside of there. I'll visit that later. So power enable, we're gonna just stick right here, and then we will wire it up like that. And then I think if we come over here and we do update PCB from schematic. Okay, changes to be applied. Add net power block, power enable, reconnect, change our value, R4 value, change our R1 value. Yep, we made those changes. Okay. Net serial, power enable. Yep, these all, I believe, are what we are looking to do. Okay. And let's do update PCB. And now it's going to create some new connections that we need to make. And so one of those should be, we should have a power enable here. Yes, we do, but it doesn't look like it. It says it's supposed to connect to anything. Let's come down here. Power enable goes through a resistor to 5 volts, which is true. But they don't, there's no electrical connection between them. So it's got the net names correct. Oh, I know why. I know why. I don't know if we can fix this right now. Okay, so this is a hierarchical pin, which means when we come back out, get out of here, wire. When we come out to this level, we can take, and we should, how do we do that? There's a way to, so sorry, let me explain what I'm thinking instead of just stumbling around. So you can see that inside of this block here, we've got VUSB, USB data in, positive and negative, and then out of that we have TX, RX, DTR, and RSC. When we come into this section of the data sheet, come on, like, why are you giving me such a hard time here? You can see like these are hierarchical pins that we expose, And so what I need to do is I need to have them show up on this block here. And there's a way to do that. And I import sheet pins. There we go. There's my BCD. And then it should also give me a power enable. What happened to my power enable? Ah, power enable right there. Okay. And now what I need to do is I need to take these over to here. And then they'll be same thing. So like import sheet pins. You'll see I'll get the power enable here. And import sheet pins. Oh, I've only done the one. And so what we would do, I'm just going to do this quickly. I'm going to clean this up. But if we bring this up here and connect it like that, and then hit save, and then come back over here and do an import. Now we should get, there we go. I just saw the line up here. Now we get a line that goes from this power enable right here down to this power enable right there. And so we need to, in our layout mode, that line helps remind us, oh, we need to make that connection electrically. And you can see there's a bunch of them right now on the board, like all over the place. All of those, with the exception of the power enable, all of them are ground. And we can fill, we can get rid of most of those. So let me just run the electrical connection, the rules check. If you run this, it'll say zone fills are out of date, refill. I'm going to say continue without refill. And you'll see 72 unconnected items. So I'm going to close that. All I have to do is, I forget the shortcut, control, fill zones, B and control B. Yeah, okay. So if I just do B, it'll do all my fills with copper. And now you can see all of those lines disappeared. If I run the DRC check again, you'll see unconnected items 3. 3 is higher than I would have thought. Pad 2 of R10. So the power enable one I would expected. Pad 2 of R5 and R8. These are probably, because I changed, yeah, I know what those are from. Because remember, we changed what was pulled up and pulled down, so we're going to have to, and you'll see these lines right here show the changes that we need to make. So it's not a good idea to, and then you can do control B, will unfill everything. And it's easier to see when it's unfilled. You should fill at the very end, but you don't want to constantly fill because you're moving. KiCad will fill around your traces. So like, let's just zoom in and do this one more time. You can see these are the traces that I've routed throughout the board. Now, if I hit B to fill it, it has this keep out, and these are all defined as part of your settings. So it keeps the copper pore a certain distance away from those traces. Well, if you've got the pore there and then you're trying to route new traces, like it's impossible. So you unfill it, get all your traces where you want it, get all the electrical connections made, and then you do your fill at the very end, and then make sure that it didn't fill in areas that you didn't want to, and that's kind of the last step. So we leave it unfilled for now. And yeah, let's go back to the schematic. So I'll make this nice and pretty, and I'll grab and the reason I like doing it this way with the hierarchical pins, because you can do like a global pin as well, and then just reference it from inside one block to the other. The reason I like to use hierarchical pins in KiCad is because it shows at this top level view, it shows how the different parts of the schematic actually connect and affect each other. So right now, like this is just the USB in, and you can see out of that, and there's a bunch of stuff to it. Let me come in here. Like it's the micro USB connector, but there's also a fuse, and there's an inductor here, and there's a bunch of capacitors and some TVS diodes and a bunch of stuff that has to happen for USB to come in cleanly. But out of that block, really all we care about is 5 volts, USB positive, USB negative, the D plus and D minus lines. And those feed into this block right here, which is the FTDI chip. And so it gives you an idea of how I like it because it shows explicitly how the components are connected to each other. And so it's just a personal preference. So that's it. I'll do the rest of this. Like I said, I'll probably make this block a little bigger so I can fit more things, the power enable and BCD on here. Wire that all up. We've already changed the resistors to be the right values. And then I think we're done with the charging stuff. I'll review it one more time, and if I find any mistakes, I'll talk about it next stream. But that's gonna do it for today. Next up, we need to move. Well, next up, we have to move a couple of things. I talked about that. We're gonna move a couple of these resistors down here. Obviously, because of the changes we made today, we're gonna have to get rid of some things in here and move them and replace them. You can see it's pretty tight. Really kind of a puzzle. I like that part of it though. It's fun. It's frustrating at times, but it's fun. So we need to move a few of those things, and yeah, we'll just connect all the things up, get the traces going, so we can get another run of these off. What we're trying to do within right now, it's Chinese New Year, so China's shut down, and what we need to do is get all these changes ready, so as soon as China opens back up, we're ready to send off a run of 5 of these to test all of the changes that we've made, test the charge current and all that other stuff. And so we need to get that finished so that we can do that right when China opens back up to get this fabbed and assembled. And I'll show you all that when we get there. So Bellum, really appreciate you joining, man. Feel free to drop in anytime. Love having extra people here, and hope you're doing some cool stuff as well. If you're doing any projects or anything, would love to hear about them. But anyway, yeah, thanks for joining. And everybody else that's watches this after the fact, thanks for joining. If there's anything in here that you didn't understand, you have questions about, send questions over. I'm happy to try and address them through the process of getting all this work done. So the idea is to hopefully help other people as well by exposing the process that we have to go through to get a product working. So that's going to do it. Thanks for watching, and see you next time.